Welcome to the second part of my annuities lecture. In this lecture, I'm going to talk about deferred annuities, forborne annuities, general annuities, perpetuities, and continuous annuities. A deferred annuity is an ordinary annuity where the first payment is made after a given number of periods. So take the example of two parents buying an annuity for their daughter's education. Assume the child is 11 years old when the annuity is purchased, and there are no payments back to the annuity owners until the child turns 18. In this case, the annuity is deferred for 7 years, earning interest in the meantime, and the payments are made during the child's time in college, let's say 5 years. At the annuity's term, 12 years from the purchase, so in other words, the 7 plus the 5, all the money has been distributed back to the parents, who are presumably using the money to pay college bills for their daughter. So I drew the picture here. This is where the annuity is purchased, and then in general, this is not the particular example, but in general, and then you have this deferral period of M periods, and then the annuity starts to get paid back to whoever purchased the annuity over so many periods, N in this case. And the amount is R, whatever, dollars, whatever, euros, for each period. And that's what I've just summarized here in this bullet list. The annuity is purchased at time 0. There are N payments, 1, 2, 3, up to N, each in the amount of R. The payments start at the end of period M, which would be M, well, the end of period M would be time M plus 1, and the interest rate per period is I. So let's see how to compute this. We already done this computation here, so it's a matter of computing the growth in the initial purchase of the annuity, and then that gives you that much more money to be distributed during the distribution period. To compute the overall present value purchase price of the annuity, we compute the present value of each payment. To cover the first payment at time M plus 1, we ask the question, how much needs to be invested at time 0, given this deferral period that we have? So if we call that quantity X sub 1, then we need X sub 1 times 1 plus I to the M plus 1. In other words, the accrual, the interest of this amount equal to R after M plus 1 periods. That's why we have this equation here. And then we just solve for X sub 1 and we get this quantity here. So if we have this amount, if X sub 1 invested at time 0 will be worth R at time M plus 1. Using similar reasoning, the present value of the second payment is R times 1 plus I to the minus M plus 2, and so on. Thus, the present value for the annuity is this sum here. And we can factor out this first term. And then we get 1 plus I to the minus 1, and so on. This is a finite geometric series. We've seen that before. So this is the sum of that, and then this just carries over. So that's our solution. We have a slight variation. If the interest rate is assumed to be different in the deferral period, call it J, from the rate during the payment periods, call it I, then we get a more general equation for Q. To be clear, it is assumed the interest rate changes from J to I after the first payment. This is almost the same as the previous equation. What's the difference in both? So this is just the interest basically during the deferral period. So there's a J there, and then the rest of the equation is the same. So let's solve our college example. given now that we have the equation for the solution. So m plus 1 is 7 years times 12 months, so 84, which means that m is 83. Then n is the period where the payments are being made, so that's 5 years times 12, that would be 60. Then I and j are the same. We don't change the interest rate from the deferral period to when the money is being paid out. So that's approximately 0.0416. And assume that $2,500 per month is needed during the child's college years. So R is $2,500. So that I didn't state that in the initial problem, but we need to make some assumption for R in order to do the computation, since we want to know how much the parents have to invest initially. So now we have all the numbers. We have R, which I plugged in here, the 1 plus the interest rate, I plug that in here, to the minus 84, that's our m plus 1. Then we have 1 minus the interest, 1 plus the interest rate raised to minus n, where n is 60. So I plug everything in here and use a calculator, and you see that the amount is $93,811.97. Then in a variation, assume that during the deferral interval, the interest rate is 6% and just 4% after the payment starts. So our J would be 0.06 divided by 12. So that would be here. And then this number for I is also different. We would use the second formula, and I didn't write it all out here, but I'll leave that as an exercise. But basically you're plugging 0.005 in here, since this would be J, and then you're plugging a different number for I, the 0.03. The little bar just means the 3's repeated indefinitely, so you might want to add a few 3's just to get more accuracy. And again, you'll get this number here. Our next topic concerns something called general annuities. That's where the compounding and the payment periods for an annuity do not coincide, unlike the case of simple annuities, which we've been looking at up until now. The problem can be solved by converting the general annuity into an equivalent ordinary simple annuity where the compounding and payments are on the same schedule. If we assume that compounding and payment times are equally spaced throughout the year, thus if compounding occurs S times per year, it occurs every 1 over S years. And if payments are made T times per year, they occur 1 over T per year. In general, if compounding is done S times per year with interest rate I per compounding period, and payments are made T times per year, we seek the equivalent interest rate per payment period, denoted by J. So this is what we get with the S compoundings per year. We want to know if we do it T compoundings per year, what's this J here that would give us an equivalent payout over the course of a year. So this is, the hard part is realizing this is the equation we want to work with. Then the easier part is just solving for J. We take 1 over T power on both sides, so that this side becomes 1 plus J, and then this side becomes 1 plus I S to the S divided by T power. And then we just subtract the 1, and we get J. So this is the case for compounding. We could also have continuous compounding. In that case, we need to solve this equation here in terms of J, where R is the nominal interest rate related to our continuous compounding. And we do a similar procedure here. We take the 1 over t power on both sides, then we subtract the 1 from both sides, and we get this equation here, which we could also solve for R, which I show here. That's just a matter of adding the 1, taking the natural log on both sides, and then multiplying by t on both sides, and we get this here. So for example, 6% compounded monthly, we have t equals 12j, which is 12 divided into 0.06 is 0.005, is equivalent to R equals, just plugging into this equation here, 0.05985, so it's equivalent to 5.985% compounded continuously, which you would expect. You get a little bit more with continuous compounding compared to monthly compounding. So you would need a smaller interest rate to get the same amount at the end of the year. I have an example here. I'll compute the accumulated value of a general annuity with terms 11 years, where the interest is compounded 5 times per year at a nominal annual rate of 5%, but the payments into the annuity are made 7 times per year in the amount of $1,000. So we want to convert this rate here from 5 times a year to whatever would be equivalent to 7 times per year. So first we just note that I is 0.05 divided by 5, or 0.01. Then we use our formula from the last slide to compute J. So this is the equivalent interest rate if we compound it 7 times a year. Now we have everything under the periods 7 times per year, so we can use our formula for simple annuity. We have the interest rate is the number we just computed here. The N, it's 11 years, 7 times per year now, so it's 77. The amount is 1,000. Then we have our formula for a simple annuity. We plug in all the numbers, and we get 200,138.73 cents. We can solve the same problem under the assumption of continuous compounding, and we use the second formula from the last slide. We plug in I and T. We get a slightly different rate here from this. And then we plug that into this formula, and I didn't show the full computation, but we get a slightly larger number than the other result, which is expected, right? You would expect to make a little bit more with the continuous compounding. So on the last slide, we did the conversion for an annuity where we were paying into it for a period of time, and then we had a payment at term, amount of money at term. And this is the other case where you have a discounted value. Basically, you want to know how much to put in to the annuity initially so that you can have payments over a given amount of time, and then eventually you deplete all the money in the annuity. And we can use the same conversion for interest rates, as you'll see in a second. So the problem is compute the discounted value of a general annuity with 13 years, where the interest is compounded 12 times per year at a nominal rate of 6%, but the payments out of the annuity are made 26 times per year at an amount of $500. So we need to convert between these two periods, one 12 times a year and another 26. And we have the formula for that. So we first compute I based on the 12 times per year, and it's 0.005. We want to know what's the equivalent interest rate if we do the compounding 26 times a year instead of 12. So we have our formula from the previous slide, and we get this number here. Now we have everything that we need to compute the discounted value of a simple annuity with per period interest rate this here. In other words, period 1/26th of a year now. N is 26 times the term, 13 years, 338, and the payout at 26 times a year is $500. So we plug that into our formula. This is from the previous lesson. We had this formula here. So we plug all our numbers in to get this here. I was able to compute this with a calculator. I raised this number to the 338th power. I took the reciprocal. I subtracted it from 1. I multiplied by 500, and then I divided by this, and I actually got this number. This little bit here, the cents, is rounded off. It was actually slightly less than 55 cents. We have another type of annuity here. It's called a perpetuity. It's an annuity in which regular payments begin on a fixed date and continue indefinitely. It is sometimes referred to as a perpetual annuity. The analysis of a perpetuity is straightforward. Suppose an initial investment of S earns an interest rate of I per compounding period. If the interest earned each period is withdrawn, then the investment can support a constant payment of R equals I times S at the end of every period forever. So you're basically just distributing the interest and not touching the principal. Equivalently, if a perpetuity pays R per period and the interest rate per period is I, then the required initial investment is S equals R divided by I. I'm just solving this equation here. This relationship can be interpreted in two ways. As a funding problem, how much capital is required to generate a fixed payment indefinitely? As a valuation formula, the present value of a perpetual stream of payments. If less than I times S, this amount here, is withdrawn each period, then the principal will grow over time, allowing the payment to be increased in the future. For example, to account for inflation. In practice, such idealized investment instruments are not directly available. However, endowment funds, for example, scholarships or charitable foundations, are conceptually similar. In these cases, the return is not guaranteed, and only a portion of the investment income is typically distributed, while the remainder is invested to maintain or grow the fund. So you might have your college may have, I don't know, $100 million endowment, and maybe they're making a conservative amount, say 5% a year. So they might only spend 4% or 80% of the interest that they're making, and then take that 20% and put that back into the endowment, so that they would eventually grow the endowment, and of course they would have contributions coming in also, but just from their investment technique, they would grow the endowment, and then that would adjust for inflation. Okay, so this is pretty simple in principle. I have some example. I have an example here of our perpetuity. Suppose a scholarship fund is designed to provide annual payments of $5,000 indefinitely. So this is maybe for an individual. If the fund earns 4% interest per year, how large must the initial endowment be? So we just use our formula from the previous slide, 5,000 divided by the anticipated interest rate. So you would need $125,000 initial investment, and assuming this interest rate held, you'd be able to take $5,000 out every year forever. So I have a remark here. The formula can be viewed as a limiting case of the present value of an annuity as the number of payments becomes arbitrarily large. Recall that the present value of an annuity with n payments is given by this formula here. So doing a little bit of calculus, if we take the limit as n goes to infinity, this number, this is 1 over a number raised to a power, but this number is bigger than 1. So this is going to go to 0, and then you're just going to have r times 1 minus 0 divided by I, or r over I. So that's the limiting case. We have another type of annuity. It's called a continuous annuity, and the math here gets a bit complicated. I'll try to go through it slowly. A continuous annuity is a type of annuity where payments are made continuously, but interest is compounded for some given period. So discounted present value is what we want to compute here. To compute the present value formula for a continuous annuity, we start with a finite number of payments m within a given compounding period, and then take the limit as m approaches infinity. So I've kind of drawn this here. You have your periods, n periods, and then the payments, at least as we're starting here, this is not continuous yet. We're instead of paying out r, we're doing r over m. So we're doing m payments per compounding period. So to that end, start with an annuity that distributes n payments in the amount of r, which I just mentioned here. So r here. Interest is compounded at the end of each period at rate I. Recall from earlier that the current value of such an annuity is given by this here. So we've computed that, and we actually sum this up. Next, we assume m payments in the amount of r made during each compounding period, which is what I just described here. Okay, so this is our initial amount that allows us to make these r payments in the amount of r at the end of each period, and now we're going to change it and assume n payments in the amount of r over m are made instead over each period. So you notice when you add these together, you have m of these, and so m times r over m gives you r. So it's the same amount of money, it's just that it's being distributed and m times during this period, and same for the next period, and so on. We define the mini period rate j so that m compounding steps produce the same growth as one period of growth at rate I. So these mini periods, as we shown in the diagram, there's m of those for one of the regular periods, and the formula that we've looked at before is we want to have 1 plus j to the m equals 1 plus I to the 1 power. So this is j is of course a smaller number, it's over a smaller period of time, but we want this effective rate to equal 1 plus I. We'll just take the 1 over m power on both sides, and we get this equation here, which we're going to need in a second. Then we note there are m times n mini periods, payments, over the entire term of the annuity. The present value of the annuity was the m payments per compounding period, is given by this here. So we're using this 1 plus j, since that's that's the rate at each mini period, and this is the payment at each mini period. So we're just discounting it back to times 0, and we have m times n of these. But we've solved for 1 plus j in terms of I, and so we have 1 plus j to the minus 1 is, for example, 1 plus I to the minus 1 over m. And then 1 plus j to the minus 2 is 1 plus I to the minus 2 over m. And you just do that all the way across. And we can write this in terms of a summation. It goes from, I use the index x, goes from 1 to m times n. That's the number of terms we have here. And then each term has this form here where x is the thing being incremented. So to get the formula for the present value of an annuity with the continuous number of payments in each compound period, we take the limit of the above expression as m goes to infinity. So we're basically taking these mini periods and making them be an infinite number. And it does converge. We don't get an infinite value here. So instead of q sub m, we're going to call it q sub infinity. That's basically q sub m, where m goes to infinity. I'm just plugging this into here. Then I factored out the r, since that doesn't involve an x, so we can factor that out of the limit. And we have this here. And this is basically the Riemann sum for this function, 1 plus I to the minus x between 0 and n. This is basically the definition of an integral in calculus. It would be this here. I need to continue on the next slide. I'm going to copy this and as the first item on the next slide, and then we'll finish this off. Okay, so this is where we left off. We've reduced the problem to this integral, and I'll show you how to solve this on the next slide in case you're interested. If you're not interested, I'll just kind of give you the answer. The first comment I made here is something I mentioned on the last slide. The second summation in the above sequence, so here, is the right Riemann sum of the function 1 plus I to the minus x from 0 to n. So I'm just explaining how to get from here to here. The typical delta x used in Riemann sums is effectively replaced by 1 over m here and here, which approaches 0 as m approaches infinity. So that's the same as letting delta x go to 0. Solving the definite integral, this integral is equal to this. Again, I'll show you how to get that on the next slide. And then we just need to plug in n for x and then subtract from that x set to 0. And when you do that, you get this expression here. And so this actually gives us the solution to our problem. We can plug in our numbers, and this will give us the an annuity with continuous payments. And if we know the final result, in other words, how much money we need to purchase the annuity under these conditions, and we know I and n, then just as we've done in other cases, we can solve for r. It's just a matter of multiplying by the reciprocal of this on both sides, and we get this equation here. Okay, so if you're interested in the calculus of doing this antiderivative for this function here, I'll show you that on the next slide. And if you're not, then I would encourage you to just accept this as the solution. So let's look at the next slide. So let's look at the calculus we need to solve the problem. We're going to find the antiderivative first of this function, 1 plus I to the minus x. We have this identity, a to the ux equals e to the ux times log a. And then we can use that on this here, where u of x is minus x and a is 1 plus I. So we have this identity. And the reason we want to write this in terms of the exponential is we know how to find the derivative, any derivative, I should say, of e to the kx. It's just 1 over k e to the kx. And then we just plug in k is minus log 1 plus I. And so I've done that here. Just plugging things in. We just get this equals this here. And since this equals our original function, just plug that back into here and we get this. And then on the previous slide, we had a definite integral from 0 to n. And that means you need to plug in n for x and then subtract from it 0 plugged in for x, which was just 1 over log 1 plus I, and we get the solution we had from before. As an example, let's consider two different scenarios. In scenario A, we have ordinary simple certain annuity with n equals 60, equal payments of $10,000, and an interest rate of 0.5% per period. So I'm kind of thinking monthly. I didn't bother to give you the yearly and then divide by 12. I just gave you the monthly rate here. And then scenario B, annuity with continuous payments over 60 periods with an interest rate the same, 0.5% per period. The continuous payments equal $10,000 in each period. So for scenario A, the present value of the annuity is here, just using our formula that we've derived earlier. So just plugging in the numbers, 10,000, 0.005 minus 60 divided by that rate, and we get this here. And then we have the continuous payments. And the only difference was this denominator was log 1 plus I. We plug that in and we get a slightly larger amount, which we would expect, right? We're getting the money as soon as it's been computed continuously. So the present value of the annuity in scenario B is larger than the present value in A, as I just stated, which is to be expected since payments are effectively distributed sooner in scenario B. And then just to compare these two numbers here, since log of 1 plus I is less than I for I greater than 0, which is the case here, right? We have 0.005 for I. The denominator in the continuous case is smaller, which explains why the present value is larger. It's also possible to accumulate value with continuous investments into an annuity. We first consider the case of M mini investments, and then we'll take the limit as n goes to infinity, just as we did before, into the annuity in the amount of R over M during each compounding period. This is basically the previous situation, except that the payments are accumulated forward rather than discounted. If the interest rate for each compounding period is I, then using the same calculation as before, the equivalent interest rate for the mini period is a J equals 1 plus I to the 1 over M minus 1. The accumulated value of the annuity is given by here. This is R over M, this is the first one, then R over M basically was the principal and the interest over that first mini period and so forth, and all the way up to M times N minus 1. That's the number of terms we have here. And we factor out the R over M. We get this series, which I've written in summation form. To get the accumulated value of an annuity with continuous input, we take the limit as n approaches infinity, as I mentioned. So we take this result here. We take we call it S sub infinity, just the way we had q sub infinity before. We take the limit as n goes to infinity. We plug this in here. We factored the r out. This all looks very similar to what we had before. And then this is the Riemann sum for it's equivalent to this integral here. Let me continue on the next slide. But this is the key point, that recognizing this is the Riemann sum for the for this integral as m goes to infinity. And just copy this from the previous slide. And what we want to do is evaluate this now. And as I explained before, this is the second summation. This one here is the left Riemann sum of the function 1 plus I to the x from 0 to n. In other words, this equation here. And thus taking the limit as m approaches infinity and 1 over m goes to 0 yields the stated integral. Solving the definite integral, we get this. I won't go through the details of the calculus as I did before, but it's a similar calculation. So we compute the antiderivative, then we have to plug in n for this, and then subtract x equals 0 plugged into this, and of course that's just going to give you 1 over the log of 1 plus I, and that gives you this result here. Okay, so very similar to what we had done in the first case. In one case, we were withdrawing money from the annuity, eventually getting to 0, and in this case here, we're adding money continuously. And I have an example of this on the next slide. So I have an example. We're going to look at two different cases, comparing the accumulated value of an ordinary simple certain annuity with 120 investments of $5,000 at an interest rate of 0.6% per period to a continuous investment with annuity with the same parameters. So these are the two equations. Again, we derived this before. This is the one we just derived. And the only difference is in the denominator here. So we plug in 5,000, the interest rate, 1 plus the interest rate raised to 120 minus 1. Then in this case we get 0.006, and in this case it's just a log of that. And again, you notice we need slightly more money here. We get slightly more money at the end of at the term of the annuity because we're continuously putting money in, which I've stated here. The accumulated value in the continuous case is slightly larger since money is deposited sooner, i.e. during each compounding period rather than at the end of each compounding period. Keyword here is during. Okay, so that was it for this lesson. I have another lesson on annuities, which I'm not going to have new material, but what I have are two different things. I've written some Python programs that can be used to do some of these calculations. So I'll describe those and I'll point you to where the code is. It's the same location as I've been pointing to before. And then I have a number of exercises, some of which we can solve using the programs I supplied.